Hello, Year 11. This is the first time I've done this, so apologies if I mess this up. What this lesson is looking at is your first lesson after the energy topic and moving on to electricity. And this lesson focuses on static electricity and static charge. Highlighted from the test as being something which a few of you need to go over. So hopefully this will give you a good breakdown of the information you need behind static electricity, and then also a couple of worksheets for you to have a go at and work through and see how you get on. I've done it so that they will last you the lesson this week, but then also half term next week. I probably would have set you a Seneca on it as well, but I appreciate that you had quite a lot on with the tests just before closure, and then I can imagine that you've got quite a lot of work lumped onto you from other subjects, and so I'm not looking to overload you at all. So in the first week back, hopefully if we're back after October half term, then be able to have a look at exactly what's what. I would have liked to have got through more of the material prior to your mock exams or internal assessments in November, which is going to be based on a paper one. So this is in paper one content. So we'll just have to see how our lessons go and whether how much face-to-face time we'll have, and whether I do need to keep it more as online learning. What I've done on this slide is I've lifted straight from the specification all of the information that you need to know for static electricity and static charge. This is just a bit of a summary, so if you want to have a read through this in more detail, you can just pause the video and then you can read through it and see exactly what's what. I'm just going to move through this lesson. You can either watch it through me. I'll upload this lesson, the PowerPoint, to the file section of Teams as well, so you can go through it in your own time, as well as then setting you the worksheets as assignments. See that's for the Van de Graaff generator. If you're not sure what the Van de Graaff generator is, then there's a picture of one on this starter activity with that person touching it with their hands. This is just a little starter activity I use with groups, because I tend to find that people do already know some information about static electricity. It just might have been that they don't know it's linked directly to the topic. So I would have hopefully have got the Van de Graaff generator out in the lesson, but obviously wouldn't have been able to with the current situation. But if you've had a go with it before, you can hopefully get someone's hair to stand on end or pass on what people refer to as electric shocks round the chain. You can pause it if you want, have a go at this. The examples of static electricity on here that we can see, you've got a person taking off the jumper right in the center of the screen at the bottom. Some people find if they've got a nylon jumper and they take off their jumper, as the jumper's rubbing against their hair, then afterwards it can leave their hair a bit static, as people refer to, so it's sort of like sticking up a little bit. Photocopiers on the right hand side, just like the photocopiers we use at school, the printers, when we scan something, it's actually static electricity which allows the toner, or the ink, that's the word for it, toner, in laserjet printers to stick to the pages. A lightning strike is actually a build-up of static electricity due to the water particles rubbing and moving over each other in the cloud, so you get a build-up of static electricity. Air is an insulator, so that means it doesn't conduct electricity, but during a lightning strike, the static electricity builds up to such a high potential difference with the ground that it actually goes across the insulator as a lightning bolt. And that's exactly what happens when you go to touch a door handle, say, and get a little static shock, which we will talk about in more detail throughout the lesson. You've got a person with a duster there. You used to get this more with plasma and LCD TVs when they first came out. You used to get a little special cleaning cloth to help reduce the static electricity so that the dust particles didn't stick to the TV. And then at the back there, clean smoke. So it's actually a way that we can reduce the amount of bad stuff essentially going up into the atmosphere through chimneys in power stations. You don't need to know it in any more detail than that though, so I won't go into it in any more detail than that. So be able to understand static electricity and its effects. How would we produce static electricity? Explain the effect charged objects can have on each other and why, and so then some key vocab in there as well. The first thing to point out from marking some of your answers in the assessment is the third point down in the key vocabulary of electrons. There is no such thing as a positive electron. All electrons are negative, and in static electricity it's only electrons that move, which if something gains electrons it will become negative. If it loses electrons it will be left as being positive. So there is no such thing as positive electrons. So please delete that from your memories, delete that from your brain, because there is no such thing as positive electrons when you're looking at the topic. Bit of a glossary there. Same again, you can pause it and read that if you wanted to. So where does static electricity occur? Some familiar events that they have in common: lightning strike, dusters that can attract dust, crackling when combing your hair, cling film when it sticks to your hand, dust being attracted to television screens, clothes clinging to each other in a tumble dryer, getting a shock after rubbing your feet on a carpet and then touching a metal object. All these events are due to static electricity. So what causes it to occur? This is one of my favourite teaching tools when I'm teaching this topic. I know you all think I'm a loser, so obviously this fits right in with it. If you go to that website, you can do it online. You don't have to download it. I won't go into it now. I'll just let you have a look at that in your own time. So same again, if you want to just go to that website, it's worth having a look at. Even though it sounds and looks stupid, it is actually very scientifically accurate. So static electricity is due to the build-up of electric charge. It's called static electricity because the charge is unable to flow. So when we're talking about something being static, we're talking about it not moving. So it might have been the case that sometimes if you're walking on a carpet, or if you've been on a trampoline, is another good example that I find a lot of students have done, is that then when they've gone from the trampoline or the carpet and touched a metal door handle, they'll feel what they refer to as being an electric shock. The more accurate term would be a static shock, but I understand why people would say that, okay? And so lightning in nature, as I said earlier, is a perfect example of this. We get a buildup of static electricity in the clouds due to the particles rubbing together, and then that potential difference builds up so that it goes across the insulator of air to Earth. So what causes it? Well, if we have got the example of combing your hair, then all of the electrons will move from one of the items to the other. So if I stick with the example of combing your hair and with this diagram in front of you, you can see that when the comb has gone through the hair, the friction between the comb and the hair, friction produces heat. So basically that energy is taken and used by the electron to move from one object to the other. Because the comb has gained electrons, that has now got an overall negative charge. So that would leave your hair as being an overall positive charge. If you imagine that each hair individually is positively charged, what do positive charges, well, what do same charges do? They repel each other, which is what makes your hair stand on end, which is why it can leave your hair being a bit static if you were to overbrush it, for example. So bringing this back to what we all know in terms of the structure of the atom, in the nucleus we've got our neutrons, which are neutral, and we've got our protons, which are positive, and orbiting or going around the outside in clouds are our negative electrons. It's only electrons that move, never anything else. And as I said earlier, and I'll keep repeating it, there is no such thing as positive electrons. So if something gains electrons or gains negative, then it becomes a negative charge. If it loses electrons, then that means that it would be positive. Because to start with, your atom, just like this diagram here, I've got 2 protons which are positive, 2 negative electrons, so the overall charge is neutral. Therefore, as soon as electrons were to move, if it gains electrons, it becomes negative. If it loses electrons, it would become positive. So the negative charge can be transferred from one material to the other. Nothing else moves, only negative electrons. I know I sound like a broken record. I will continue to do so because, as I say, from marking your assessments, it's quite obvious that some of you weren't quite sure on this, so I just want to make sure that it's hammered home for you. I would say those 2 bullet points are the best 2 to write down. So one material ends up with more electrons, so it's now negative. one material ends up with fewer electrons, so it is positive. Again, this is normally where I do a couple of different demonstrations. The Van de Graaff generator we've already talked about. A ruler with a stream of water, that is something that you can do at home. If you just get one of your normal plastic rulers that you have, either a 15 centimeter or 30 centimeter. If you get yourself the best material is nylon, so something like sports tops or sports shorts, that sort of material, and essentially rub them together to build up static charge in the ruler. If you then turn your tap on very slowly, so you've got a steady stream of water, but make sure it's not on too high. If you gently move your ruler very, very close to that water, you should be able to see an effect that happens. If nothing happens, then you can watch a YouTube video for it to see. Balloons, at some point in your life, you've probably rubbed one on your hair to make your hair stand on end. So again, the same thing. In a hole puncher, piece of useless quiz knowledge for you, the bits of hole punch that are stored in it are actually called chads. But if you do what I said with a ruler earlier, in terms of rubbing it with a sports material or something nylon to charge it up, and then bring it close to tiny bits of paper, you'll be able to see the effects of static electricity there as well. So it's when two insulators are rubbed together. So we can get a negatively charged rod and a positively charged cloth. So if they're rubbed together, the electrons have moved from the cloth to the rod, and that's what's made it positive. If this was to be done with something that isn't an insulator, so we would call that a conductor, so something that conducts electricity, we wouldn't get that build-up of electrons because it conducts electricity, okay? And I believe that was also one of your questions in the assessment, and that's also why you have an earth wire in a plug, because if something was to go wrong and the electricity was to go live, then it would travel down the earth wire to earth. The two things to always remember about electricity: one, it's lazy, so it takes the path of least resistance, and the second thing is that it wants to get to earth. So it will always take the easiest route, so the path of least resistance, and then it will always try and get to earth. The other thing we mentioned earlier, like charges repel and opposite charges attract. That is a very, very frequent one marker in some guys in questions. So when I say guys, I just mean it might be disguised as something else asking you, but essentially just to remember that like charges repel and opposite charges attract. This is something that I normally do as a demonstration to get two balloons to repel each other hanging from like two stands or something. And in terms of what the fields would look like, again, I think this was a question in the assessment that you had. Firstly, if a question asks you to draw 3 arrows, make sure you only draw 3. I had some people draw more than 3, and I had some people not even draw 3. So make sure you follow the instruction of the question. The second thing is to remember that the electric field goes from positive to negative. So on the left-hand side, because it's a positively charged object, the field lines are coming out of it. Notice that they're acting perpendicular to the surface of that object. So in this case, the easiest way to think of it and draw it is like a crosshair. So like you can see there, like a cross and like a plus sort of thing. So you've got them going up perpendicular to the surface of the object. For a negatively charged object, then the arrows would be going towards the center. And as you can see there, the direction. Always draw field lines perpendicular to the surface, and always draw at least 4. Your question, you were given 1 and asked to draw 3 more. So it might be a case that you're given a blank object and you've got to just draw them on yourself. So try and always make sure you draw at least 4, okay? Why do you think this is an example of a non-contact force? Well, I'll let you have a think about that for yourself for a few seconds. Either pause it or you can just wait. But it would be classed as a non-contact force because you can feel the effects of an electric field without actually touching the object. So this is linked to do with induction, which we'll look at in the future in terms of how we generate electricity. But we can pass a wire through an electric field and a magnetic field and actually get an electric current. So it's a non-contact force because it doesn't actually need to be touching something for us to feel the effect. I've attached 2 worksheets. They're both they're not short, but they're not stupidly long. They're good mixture of questions in terms of the amount of challenge for you to work through. What I've tried to do is cover all of the material that you need to know, and then also be able to give you the chance of applying that knowledge. I know it's rubbish that you haven't got your assessment back and your marks and everything along those lines. So I'm hoping as soon as October half terms finished, we'll be back together in the classroom. However, if we are in the case of further lockdown, we'll just have to do the best that we can with our online. Okay. There's a bit of an animation there about a Van de Graaff and how it works. You don't need to know that. I just tend to show it as another example, because essentially that belt moving is what produces the transfer of the electrons to then stand on end. Just as a little plenary for the lesson, I normally do this as well. No more than 30 words. Explain how we get a buildup of static electricity. Okay.